Okay, so finishing up section 15.2 and going into section 15.3. And 15.2 was principle of linear impulse and momentum for a system of particles. And 15.3 is conservation of linear momentum for a system of particles. Okay, so just some questions associated with this, but you could actually come up with and define your the impulse diagram. And here's the impulse diagram for this, where it has all the forces that are being applied. And you have to consider, of course, the force is off in the same direction of the motion and the normal forces associated with this. The last part is that the impulse due to the weight, okay, acting the opposite, acting straight down or in the y direction. Okay, another one is that you have a pile driver, and a couple different ways to look at this one is thinking about, what's the velocity of the pile after the impact, and thinking about, well, what is the difference between if the pile drives it straight down, and the other one if it rebounds to a certain extent. So what happens? What would be the impact of that if it rebounds, right? Now we would have some momentum going in the opposite direction, all right? And one of the main points of for section 15.2 was this idea of, here's the impulse and momentum equation. And this kind of extended out from what we had previously looked at, where now we have for external forces, any external forces in the system. And one of the things to note is that, all the internal forces would sum between the particles in the system would sum to zero. Okay, so like one pushes on one, the other particle would push back with the same force, right? So here would be our force of linear impulse and momentum. That includes the external forces. Impulses do those external forces because the others sum to zero, right? So it's whatever initial, the masses of individual particles times their velocities, summation of those, and here's the impulse, so the external forces, and then here's the final mass and velocities, the momentums of the particles in the system, or the summation of all the momentums in the system of the particles. One of the things we could do for a system of particles, we could define a center of mass, or aggregate particle of mass m total, where m total is the sum of all the particles. So we could do that, so we could come up with a aggregate velocity, right? So we have the momentums of the individual masses divided by the mass of the total system, and we can come up with a aggregate velocity of this of the system of particles, right? And the motion of this is based on the center of mass, and then its position can be also defined. And the way you do that is you take the individual masses and their positions and divide it by the total mass. Okay, so this one would actually describe the motion of the center of mass, right? Now, when we look at the linear impulse and momentum equation, and if we have a system where all of the external pulses acting in the system is zero, then we have just a simplified equation where we have initial momentum is equal to the final momentum. Okay, so if there's no external forces, essentially, or no external impulses, this is the conservation of linear momentum. Okay, and this one is when you're talking about how particles collide and interact, and it's actually in section 15.4. We're going to look at impacts. All right, so the way we can think about it is that we only have impulsive forces when it cause a change in linear momentum. Okay, when you have impact of particles, so like hammer and stake. Right. So in this case, if we're doing a system like this, the weight of the system stake is negligible or non-impulsive compared to the force of the sledgehammer. Okay, provided it's driven into the ground with little or no resistance, the impulse of the ground acting in the stake is considered non-impulsive. Okay, so that would be the analysis of a system like this, where we have a conservation of linear momentum. Okay, so here's a problem, first example. So we have two blocks. One block is connected to a spring and it's stationary, and we have another block that has a velocity 15 meters per second when it impacts this other block. And after the impact, they stay together, okay, which is going to be needed for our problem. So this follows the law of conservation of linear momentum. There's no external force acting on this. It's just whatever momentum this original block has or the system has, and this has no momentum initially. All this momentum after striking it is going to come up to a final momentum of the two blocks. Okay, so we're going to use that information to figure out what's the maximum compression of the spring, right? So the way to do that is, first we can think of this as a single system, apply conservation of linear momentum, which gives us a velocity. And then we can use that. So now we have, once they strike, once they hit, what's going to happen is you're going to have, whatever momentum you initially have is going to be essentially the same momentum you have right after they impact, okay? And then you can come up with a velocity of the two blocks right at that point in time. And then you can use that. That would be a certain amount of kinetic energy. So if we use the energy conservation or conservation of energy, we can translate that to potential. That initial kinetic energy of these two blocks will translate into potential energy to compress or be converted over to potential energy to compress the springs. Okay, so here's the solution. Here's the initial equation. So you're just saying whatever you have initially is equal to whatever you have final. And the thing to be, when you think about in terms of direction, you define a direction. In this case, I define a direction as positive off to the right. And so you have a negative. Here's the block, the first block, right? This is the block over to the right. This is block B, okay, which is 15 meters per second times 10, which is the 10. Block B is the 10 kilograms, and the other one's 15 kilograms. Okay, just going back and looking at that again. And then you have the mass of the two blocks, and they have some other velocity at that point. Okay, so right after impact, they have a velocity together of 6 meters per second, and they stick together. Okay, so now you have the kinetic energy of the whole system, of the two blocks, and you can use that with the conservation of energy equation. So you say initial kinetic energy plus initial potential energy is equal to, final kinetic energy plus final potential energy, right? So what's going to happen? Well, they strike. All that energy and kinetic energy gets converted over to potential energy to compress the spring. So its maximum point of compression is what we're going to look for. So initially we have this. Here is our initial kinetic energy, the mass of the two blocks. It's 1/2 mv squared. So here's the total mass of the two blocks. Here is the velocity, minus 6 meters squared. And then we have, here is our initial potential energy, right? The spring is not compressed, so we have no potential energy. And then finally, we have no kinetic energy, right? Because now it's compressed as far as it can go. And at that point, there's no velocity. It's all been converted. There's no kinetic energy associated with the block. All of it's been converted to compress the spring. And here's the spring. So the spring, 0.5 times, here's the K value, 10K newtons per meter. And here's the S squared term, right? And this is the displacement. We're looking to solve for that. So you perform the calculation, solve for S max, and you got that as 0.3 meters. Okay? And that's the solution for that one. Okay? So here's another example. You have two railroad cars, and they collide. And there's some rebounding this time, though. Okay. So B moves off to the right, and uh, B moves to the right with a certain speed after collision. Okay. Then we want to find the average impulse force between the cars if the collision takes place in zero point 0.5 seconds. So two basic parts of this problem, right? We're going to apply conservation of linear momentum because we know what the velocity of B is, but we need to find the velocity of A. So we apply that law, the equation of the conservation of linear momentum to find that velocity of A. Okay. And then use the principle of impulsive momentum to find the impulsive force. Okay. So, okay. So we have the time. So we could actually, we know that impulse is, times time, force times the time. So we're given the time. So we can actually extract the force from that. Okay. So here we go. First thing is we have momentum associated with car A, momentum associated with car B when we first start. And then after the collision, we have momentums associated with each of those cars. Okay. So here's the first one. Here's A. Here's B. And one of the things we have to pay attention is the direction of the car. So in this case, it's negative 1.5 meters per second. We're basically saying positive velocity off into the positive x direction. Okay. And then finally, we are ending up with some. Here's the mass of the car A, and times its velocity, and here's the mass of car B times its velocity, and now it's positive, of course, because it's going off to the right. Okay. So if you solve for that, you come up with 3.75 meters per second. All right, so the next thing is to apply the impulse of momentum. And now we know those velocities, or we know, so in this case, we're looking at it for for car A. So we know its initial velocity, its mass, and its final velocity. So the only part is that we're looking for is the impulse, right? So we could solve for the impulse for that. So solving for the impulse comes up 52,500 Newton seconds. And now we know what the time is. We're already given a time as 0.5 seconds. So now we can solve for it. The average force is basically average force times 0.5 seconds. So force average is 105 kilonewtons, okay? All right, and that was the problem I was actually asking for.